Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe, press the notification bell, and share my videos if you find my videos very helpful in your studies. So share them with your friends so that you can also be of help to your friends. So these videos discuss This video discusses about the solutions to problems on fluid pressure and plane surfaces. And the problems I selected are challenging ones, and I hope that you can follow the solutions. So here is the first problem. A rectangular closed tank has a square base 1.5 meters on the side. The height of the tank is 3.6 meters. It contains molasses of specific gravity 1.8, 1.8 meters thick, water 1.8 meters thick, and the remaining space is air. A gauge attached at the bottom of the tank reads 60 kilopascals. So determine the following: the pressure in the airspace, the total pressure or the force or hydrostatic force on one side of the tank, and the third one is the location of this force from the bottom of the tank. So this is the figure. Remember that the bottom section is a square 1.5 meter by 1.5 meters. So therefore the width of the tank perpendicular to the board is 1.5 meters. So we have here the height, and the molasses should be at the lowest portion because it is the densest liquid, followed by water, then of course the gas or the air. By principle, the pressure in the airspace is the same. So if we sum up pressure from the airspace down to the bottom, then we equate it to 60 kilopascals. So sum up pressure, so meaning of SUP is sum up pressure from airspace or from this interface between air and water to down to the bottom. And remember that going down is the pressure increases. So we have pressure at air plus 9.81 times 1.2 plus 1.5 times 9.81 times 1.8 equals 60 kilopascals. So solving for pressure in the airspace, it is equal to 21.74 kilopascals. So that's the answer to the first question. The second question is the total pressure or the total force or the force acting on one side of the tank. Since this is a complicated problem where we have layers of fluid and we have air under pressure, so we use pressure diagram instead in computing that force. So force is equal to specific weight of volume of force is equal to volume of pressure diagram. So we have that. So this is the pressure of air, which is equal to 21.741 kilopascals. Then the pressure here is still 21.741. So the increase in pressure is just due to water. So 21.741. So this increase is 9.81 times 1.2. We will call that P sub 1. So this intensity here, let's call that P1. And P1 is equal to, so the total pressure here is pressure of air plus P1. And P1 is 9.81 times 1.2. So that would be 11.772 kilopascals. Then finally, this is this at this interface, the pressure is pressure of air 21.741 plus P1, which is 11.772. So this increase in pressure here is down to the bottom of the tank is specific weight of molasses 1.5 times 9.81 specific weight of water times 1.8. So we will call that P sub 2. So P sub 2 is simply 1.5 times 9.81 times 1.8. So P sub 2 is 26.487 kilopascals. So the total pressure at the bottom 21.741 plus P1 11.772 plus P2 which is 26.487 is also equal to 60 kilopascals, to be clear. So we will call the force represented by this pressure of air as F1 because the height of the tank is 3.6 and this is rectangular pressure distribution, so therefore F1 acts half of 3.6, so 1.8 meters from the bottom. Then F2 would be the volume of this pressure diagram here, which is triangular. So its location is 1/3 of 1.2, which is 0.4 plus 1.8, so 2.2 from the bottom. Then F3 for this rectangular pressure diagram, and it is equal, its location is simply 1/2 of 1.8, so 0.9. Then lastly, for this triangular pressure diagram, bigger triangular pressure diagram, F4, we'll call that F4, its distance from the bottom is 1/3 of 1.8, so 0.6 for the location of the resultant later. So this is the resultant force, and we will call its distance from the bottom by y sub b. So that distance is y sub b. So force is volume of pressure diagram. For this case, we will not use specific weight barred H area because if we use that, it will be very tedious and long. The solution will be long. But we can still use that. Let's just use this simpler approach. So F1 is volume of pressure diagram. So area of this rectangle times width perpendicular to the board, which is 1.5. Perpendicular to the screen, which is 1.5. So it is 21.741 times 3.6 times 1.5. And that would be 117.401 kilonewtons. F2 is 1/2 or 0.5 of P1, which is 11.772 times 1.2 times 1.5. So it is 10.595 kilonewtons. F3 is equal to P1, 11.772 times 1.8, perpendicular to the board, 1.5. So that would be 31.784 kilonewtons. Then lastly, F4 is equal to area of this triangle is 0.5 or 1/2 of P2, 26.487 times 1.8 times 1.5. So 35.757. Therefore, the resultant force is simply 117.401 plus 10.595 plus 31.784 plus 35.757. So the resultant force FR is equal to 195.54 kilonewtons. Let's proceed to the location. So we use Varignon's theorem for this case. So the moment of the resultant, which is Fr times Yb, 195.54 times Yb is equal to F1 117.401 times 2.2, 1.8 F1 plus F2, which is 10.595 times 2.2 plus F3 31.784 times 0.9, then plus F4 35.757 times 0.6. So solving for YB is equal to 1.456 meters. So that's it. That's the solution to this problem. Notice that what is important is we generate these forces, then after that we apply statics. So for solution of problem 4, isosceles triangle gate AB in the figure below is hinged at A and weighs 1,500 newtons. So question A, what is the force exerted by the oil on the gate? Then how far is the force in A below the free surface of the oil? And third, what minimum horizontal force P? This one is required at point B for equilibrium. So without this force P, naturally this gate will open, oil will flow. So that's why there must be a force P here or a stopper. And the question is, what is the reaction at the stopper to hold this gate in place? So this is the gate, 1 meter. Then this is the force which acts at the center of pressure. And the centroid of the area of the gate is above. It is where the weight acts of 1.5 kilonewtons to be consistent. So that's CG. The distance between CG and CP along the plane of the isosceles triangular gate is, and they are aligned or collinear with the axis of symmetry of this isosceles triangular gate, is denoted by E. And the height of the gate, we will call that H sub T. Then this distance of CG vertically from the oil surface, free oil surface, is denoted by H sub CG because we can use F equals gamma of oil barred H or H sub CG times area of the gate. Now, for H sub CG, so it is simply equal to 3 meters plus, because this is straight or linear, so this is just 1/3 of 2 meters. HCG is 1/3 of 2 meters. There's no need to compute first for this location, then multiply it by sine of 50, because the result is still uh, 3 meters plus 1/3 of 2. So HCG is 3 plus 1/3 of 2. And that would be 11 over 3 meters. That's H sub CG. Then for the height of the gate, so we have here a right triangle, this one. Sine of 50 degrees is opposite 2 meters divided by hypotenuse, which is the height of the gate H sub T. So sine 50 degrees equals 2 over H sub T. So H sub T is 2 over sine of 50 degrees. So that's the height of the gate. So we can now compute the force, which is specific weight of oil, 0.83 times 9.81, barred H is 11 over 3, then the area is 1/2 of 1 meter times HT, which is 2 over sine of 50 degrees. So computing for F is 38.97 kilonewtons as the answer there. Then for the second question, how far is the force in A below the free oil surface? So that is CP, H sub CP. So it is slightly greater than H sub CG. So to analyze it well, this is the distance between CG and E. I just enlarged it. So we have a right triangle somewhere here. Then this is 50 degrees. So therefore, this is the vertical projection EV. The vertical distance between CG and CP is E sub V. Then E sub V is E sine of 50. So that H sub CP is equal to H sub CG plus E vertical. So H sub CP is equal to H sub CG plus E vertical, and E vertical is E sine of 50. Take note that E is height of triangle square over 18 H sub CG. We already derived that. And times sine of theta. Again, E is H sub T square sine of theta over 18 bar H sub CG. And E vertical is E sine of 50. Therefore, E is, this is the expression for E, height of triangle square over 18 H sub CG times sine theta. Since E sub V is this value here times sine theta, so E sub V is HT square sine square of theta divided by 18 barred H, where theta is equal to 15 degrees, the angle of inclination of the gate. So substituting that value, HT is 2 over sine of 50 quantity square, then sine square of 50, then divided by 18 times barred H, which is 11/3. So therefore, E vertical is same as the formula for vertical projection, which is height of triangle square, vertical projection of triangle, which is 2, no? 2 square over 18 8 sub cg. So even if it is inclined, the angle does not matter here because it will result to vertical projection of height of triangle square over 18 barred h, or 8 sub cg. So solving for E sub v, it is equal to 2 over 33 meters. So 8 sub cp can now be found. It is equal to 8 sub cg, which is 11 over 3, then plus 2 over 33. So 8 sub cp is equal to 3.727 meters. So next is the minimum horizontal force P required at point B for equilibrium. So we simply sum up moment about A equals 0. So clockwise positive, but before that, let's have the details, especially the distance. So if this is point A, this is distance of centroid along the plane of the gate to point A, the hinge. So therefore, this is 1/3 of 8 sub d. And this is E. This is where F acts. So the moment arm of F is E plus HT over 3. Then we have the weight here. So which acts through the CG. And this is HT over 3. Therefore, this horizontal distance or moment arm of the weight is equal to HT over 3 times cosine of 50. That distance there. HT over 3 cosine of 50. Then the moment arm of F is simply E plus HT over 3. So P times 2 clockwise plus weight 1.5 times quantity H sub T over 3 cosine of 50 degrees. Then equals F times quantity E over E plus HT over 3. Where E is equal to, where is E? E is equal to E sub V divided by sine of 50, of course. So this expression is E because E is E sub V over sine 50 degrees. Remember, sine of 50 degrees is E sub V over E. Therefore, E is E sub V over sine 50. So substituting these values, P times 2 plus 1.5 times quantity HT, which is 2 over sine 50, that's HT divided by 3 cosine of 50 degrees equals F, which is 38.97 times quantity 2 over 33 divided by sine of 50 degrees plus HT, which is 2 over sine 50 divided by 3. So solving for P is equal to 18.08 kilonewtons. So that's it. That's the solution to this problem here. So this is the third and last example for this video. The gate is hinged at A and rests on smooth floor at B. The gate is 2.5 meters into the paper or into the screen. Determine the following: the force exerted by the water on the gate, the force P needed to open the gate, neglecting the weight of the gate, and the force P necessary to open the gate, considering the weight of the gate of 6 kilonewtons this time. So this is the figure, and if you study the figure, we have a closed chamber here. Then this is the gate. Then when P is required to open the gate, take note that there will be no reaction at B. So F is acting perpendicular to the gate, but the height of the gate is still to be computed. So we enlarge that gate here, and the force is acting at the center of pressure. So sine of 60 degrees is, so imagine this right triangle here. Sine of 60 is equal to 2.598 over the height of the gate AB. So height of the gate AB is equal to 3 meters. Therefore, the gate is 2.4 meters wide, perpendicular to the screen, by 3 meters. So the centroid of the gate is acting 1.5 meters along the plane from point A. And 1.5 is half of 3, of course. So that's 1.5 meters. So this is the force F, and that distance is E along the plane of the gate. So first, let's solve for the force exerted by the water on the gate. Since we have layers of fluids, so it is challenging if we use specific weight barred edge area. Instead, we use pressure at the centroid times the area. So we first compute the pressure at the centroid of the gate. So pressure at the center of the gate is equal to negative 10 plus 0.82 times 9.81 times zero point 0.8 plus 9.81, because this is water now, times quantity 1.2 plus half of 2.598. Half of 2.598, so we can locate the CG. No? So 1.2, this distance, vertical distance to the centroid of the gate is 1.2 plus 2.598 over 2. So the pressure at the centroid of the gate is equal to 20.95 kilopascals. So we can now solve for F. 20.95, the area is 2.4 times 3. So F is equal to 150.84 kilonewtons. Then the force P needed to open the gate, so we need to solve for E first. We sum up moment about A equals 0. So the equation is F times 1.5 plus E equals P times the moment arm is 3 cosine of 60. So because this is 3, the hypotenuse, and this angle is 60, so that is 3 cosine 60 or 1.5 meters. So E is height of rectangle square sine of theta over 12 barred 8 or 12 8 sub CG. Now what is 8 sub CG? 8 sub CG is computed from pressures at CG. So pressure at CG is already computed 20.95. Then we equate it to gamma times barred H or gamma times 8 sub CG. The question is which gamma? Because it is water that is in contact with the gate, then it is the gamma of water. So pressure CG is gamma at G, gamma at the centroid, or gamma of the liquid in contact with this gate, times 8 sub Cg. So 20.95 equals 9.81 times 8 sub Cg. Again, Yg is gamma of water because it is water that is in contact with the gate. So solving for 8 sub Cg, 8 sub Cg is equal to 2.136 meters. Having found 8 sub Cg, we can now solve for E. Height of rectangle is 3 square sine of 60 degrees over 12 times 2.136. So E is 0.3041 meters. We now set up summation equilibrium equation, summation of moment about A equals 0 to solve for P. So clockwise positive, so it is F 150.84 times quantity 1.5 plus 0.3041 meter, then equals P times 1.5. Solving for P, P is 181.42 kilonewtons. So the third question is also very easy because we have set up the second equation. All we have to do is add the contribution of the weight of the gate, which is in this case clockwise. So since it acts at the centroid, so it cuts the distance 1.5, so into 0.75. So this distance is 0.75. Or 1.5 cosine of 60 degrees is 0.75. So it's also clockwise. So summation moment about point A equals 0, clockwise positive. So we have 150.84 times quantity 1.5 plus 0.3041 plus 6 kilonewtons times 0.75 equals P times 1.5. So solving for PP is 184.42 kilonewtons. Or in short, because P acts or the weight acts at the CG, then half of 6 is 3 is transmitted to A, the other half is transmitted to P. So that's why P required here is now 181.42 plus 3. So that's why it's 184.42. So that's all for this video. I hope that you will you were able to follow the solutions and understood it. What is required here is you should know the expression for E, and remember that the force always acts at the center of pressure, not at the center of or the centroid of the area. So, and another thing is if the situation is complicated, we have layers of different liquids, and we have a gas also here, then solve F by pressure at CG times area. And I hope that finding the pressure at the centroid is no longer a problem. Okay, bye-bye, and thank you for watching.